All right, good afternoon, everyone, and welcome to another edition of the Friday seminar. I am pleased to welcome Avipsa Roy. Avipsa is an assistant professor in the Department of Urban Planning and Public Policy and a faculty affiliate at the Institute of Transportation Studies at UC Irvine, a sister institution. She conducts interdisciplinary research relevant to planning smart, resilient, and safe cities. She's interested in studying the complex nature of urban systems using big data and has developed computational methods to address issues related to active transportation planning, safety, and electric vehicle charging equity in the urban context using machine learning approaches. Her research has been funded by the Haynes Foundation, by Caltrans, by the Southern California Association of Governments, and has also collaborated on projects funded through National Science Foundation and the Department of Energy. So I'm excited to hear what she has to share about spatial analysis and equitable transportation.
Thank you so much for the nice introduction, Susan. Thanks for inviting me here. So it's very interesting for me. After the pandemic, this is my first in-person talk. I would have liked. So I'm kind of still surviving from the social anxiety that we all have faced. But thank you all for gathering here. Without much delay, I would just jump into the title of my talk, which is Spatial Analytics Approaches for Equitable Transportation Planning. So as a land grant institution, I would like to just acknowledge this. I will read it out aloud, but just take a while. Thanks to the Native American landowners who have owned this property, and we've kind of acquired it from them. So yeah, let's just appreciate it. Okay, so this is my lab. I'm gradually growing it bigger. I hope to grow it bigger. So these are my students. Krista Christensen, she's a MARC second year graduate. She is about to graduate or has graduated. So she was working with me on active transportation and social equity issues. That's when we started looking at transportation equity in the Orange County context. So Casey Chung, she is an urban studies major. She's an undergraduate at UCI's urban planning department. And she's working on urban green infrastructure and sustainability. Another student of mine is Mankin Law. He's also a second year MARC graduate. He's working on electric vehicles, GIS, and remote sensing. And my first PhD student is Sheng Jin. He's from Boston University. He's working on issues related to housing affordability and machine learning. So that's my team. And I would talk a little bit about my lab in general. So my background is, I did my undergraduate degree in India, the University of Calcutta. It was a Bachelor of Science in Computer Science. Then I switched over to geoinformatics, which is a transdisciplinary field between geosciences and informatics or information science. We had a program in Germany in the University of Maastricht where it's an institute for geoinformatics. And my mentor is also the first person to establish that center right there. His name is Edson Besma. You can look it up. He's the person who developed our spatial packages. So that's my take on geoinformatics. And then I did my PhD at Arizona State University. My PhD is in geography. At this point, I'm pretty confused. What should I call myself, a computer scientist or a geographer or a geoinformatics person? But I would say I am a geographer who does computational methods. So computational geoscience or spatial data science, as we call it. So this is a little bit of a research overview that I have been working on or have been framing for the past 2 years or since my PhD duration. So I start with active transportation, where we are talking a little bit about non-motorized modes of transportation, equity issues around it, and how spatial analytics approaches can help mitigate certain infrastructure issues or equity planning issues in the urban context. And then moving on to monitoring change in ridership patterns, essentially, but change detection in general is a big problem where the spatial context is often missing, also the temporal context. So we're trying to bring that into the research, and then how built environment also plays a big role in transportation planning in general. And then how does natural hazards and extreme events influence transportation planning? So that's a brief agenda of the talk. And how do I kind of summarize so much that I just spoke in a sentence into my research thought? So that's something also which is very interdisciplinary in nature. The first thing that excited me to come and become an academic researcher was playing with data, but then also contextualizing my research in a bigger realm. So that's where spatial statistics, the field of spatial information science came in, or as we know it in mathematics. And then how could we leverage the area of geoinformation science to generate policy-ready outputs, which are also informative, not only for planners, but for the general perspective or understanding of how planning should develop and how to mitigate different infrastructure amenities for people of all, I would say, for all populations, let's just say. So just beginning with active transportation, the first theme of my research. How many of you know what active transportation term is? Have you heard of the term active transportation? Okay. Good. So active transportation in the sense that I learned it from my advisor, Tristan Nelson, was a mix of non-motorized modalities that involves physical activity. So biking and walking, that kind of helps our cardiovascular health, but also improves cultural connections, how people interact with each other. If you are a car-facing economy where a lot of people are driving cars, that's not going to go away, but post-pandemic, I've seen essentially that people have stopped lanes and opened them up for walkability purposes. So that builds community, and that kind of helps promote a lot of other thinking in terms of the planning research domain, such as accessibility, how do we think about public health, sustainability in general, and also the built environment, what role it plays in terms of summarizing these interactions. Okay, so this is a summary plot that I got from one of the story maps that I looked up for UC Davis, and I found this nice infographic which says that Davis has the highest population or mode share of biking to work, which is an interesting phenomenon because it's not very common in the US. It is very common in European cities just because by virtue of the design of the city, they are much smaller in space, very tightly integrated with transit and accessibility, but not so much here. But Davis stands out in that sense. Other than that, a lot of Californian cities fall here, not much on the East Coast or Central of the United States. But this is, let's go with this, that you'll be interested to hear more about active transportation. So when we are talking about active transportation, we have seen a lot of researchers like Ralph Bueller and people have been talking about it since 2015, not very recent. So how are we looking at these modalities? Only 50% until 2016, only 50% of US adults met the guidelines of 150 minutes of physical activity per week. So that's a regular healthy lifestyle by definition from the health folks, but not a lot of people get that privilege to use those kind of modalities. So most errands in the US are within walking or biking distances. There's 27%, which is within a 1 mile radius, and then 61%, which is bikeable, and within a 5 mile radius. So people who live in neighborhoods with sidewalks are 50% more likely to use those modes compared to other people who do not live in well-designed neighborhoods. So mixed-use neighborhoods with work, play, and shopping, there is a 33% chance that people will use active modes of transportation. And then it also helps in slowing down traffic and reducing crashes, which is mortality rates, exposure in general for all pedestrians and bicyclists. 35% of the streets face these kind of mortality incidents, and we could reduce that with more investments in these kind of transport modes. So just the first topic that I would talk about is how do we map the ridership patterns for all ages and abilities. Why mapping is important? Because it gives you a visual reference, especially as a planner, to understand where should I place my infrastructure? Where do people go? Where do people feel uncomfortable to ride? And can we have a visual evidence for it? So the research motivation for this research were three things primarily. How can we develop ways to improve data coverage for modalities that are not very common, like messaging? What are the methods to tackle bias in big data sets or crowdsourced data? And which areas will need more safe and better infrastructure? And there's a paper by Tristan Nelson on identifying traditional data and emerging data sources and what are the different comparisons. So we compared ridership, safety, infrastructure, and attitudes, which are all components in identifying better infrastructure needs from data-based analysis. So manual and automated counts often are the main data generating source for bicycle count programs. And there's an emerging source, which is wearable data platforms like Strava and such, which is a crowdsourced, mobile-based, GPS-enabled smartphone app, which captures your movement patterns. So it's anonymized, but it also captures a very well-defined transportation movement kind of a information source. It's a secondary data source, it's a passive data source where people record their trips, but they also kind of give you an understanding of where most commonly bike-friendly areas are, walkable areas are. And then in terms of safety, you have data from the police, the hospital, the insurance data, and then you also have data from crowdsourced apps like bikemaps.org, which I'll show in a while. And then infrastructure data are often found from open data portals, like the census data or the city's own open data portal. Sometimes it's just figuring out if you can gather some reference from OpenStreetMap. And then attitudes are obviously more interview-based survey and public consultation-based data sources, which are traditional forms of such data. And then a secondary source is social media. So what does the data look like when we are talking about big data in bicycling or active transportation research? So there's data sparsity. So the map on the left shows how official count data is spread out. And then on the top right, you'll see data from Strava, where you have data at every intersection and every link. So these kind of data are very dense in coverage, spatially, and also temporally because it's 1 minute coverage. But sometimes they are a biased sample. So what kind of data they're representing is not very clear unless you know very well who is collecting and how much. The bias is often in terms of the type of trip that is recorded, so whether it's a recreational or a commute trip, and then also by age groups and the gender. So females between the age of 25 to 45 are underrepresented, males are more represented. Younger population are less represented, below 25, but from 25 to 45 they are over. So it's just how many people have access to that app, who is recording the trip, and who is aware that this particular modality of data recording exists, that can kind of help capture the data. So that's how the Strava data looks like. And then what are the factors that will influence or help you adjust bias in crowdsourced data like Strava? So these are the factors that were identified across multiple cities. So there are 5 cities we work with: Boulder, Ottawa, Phoenix, San Francisco, and Victoria, which is a city in Canada. So the first 4 are United States-based cities. The top 4 variables that emerged that were important and kept popping up in our feature selection algorithm was how many people were using Strava as their source of recording data, percentage of trips that were commute trips that were recorded, what was the average speed limit, was the crash density in that particular city that's captured from another secondary data source. And then there were very other context-specific variables that popped up, which was some cities like Phoenix, where we had access to green space pop up because it's a flat city, it's warm, and how much shade people have while they ride their bikes is something that determines how much people have. So that is a context specific variable, and the other population factor that were how many, what's the white population ratio, what's the females, how many people are riding who are females, that is not very well represented. But again, for some cities like Ottawa and Phoenix, they were overrepresented, or they were the factors that could adjust the bias in the crowdsourced data. So we use a linear model to kind of use these factors as independent variables, where our dependent variable was what's the total number of bicycling ridership in a particular city. And using these adjustment factors, we corrected the bias or reduced the bias, I would say. So in terms of what variables were selected, we used a lasso methodology. It's a feature selection technique, which is a machine learning like algorithm where you don't have to choose the variables. If you have a set of 20 variables across 5 or 6 cities, the algorithm will pick the top most influential variables, in the sense the ones that explain the highest variance in data. So this might sound a little complicated. Let me simplify it for you guys. So, say for example, you have for the city of Boulder, you have these 25 factors which you give to Lasso, and Lasso will choose the top 5 that will have, it's like PCA, if you know, PCA variance-based algorithm. So it will determine if 5 variables are sufficient to express the variance in the ridership volume. So that variance explanation is not common across all cities. So the same variables will not explain all the variance in all cities in the same way, because the context, the location where we're capturing the data matters. So if it's a city which is very hilly, obviously slope will be a determining factor. If we did not have temperature variables, but if it's something that heat exposure or snowfall kind of determines how many people will ride a bike, that will get captured in the context specific feature selection. So that's the process of selecting your adjustment factors. And then we compared the rate of predictive accuracy across these different cities, and we also generated a map of the ridership volume predicted using this. We used a Poisson-based model because the count distribution was, and we have official data from the city, which followed the Poisson distribution. So in terms of seeing the accuracy, the highest was in the city of Phoenix, followed by city of Victoria, Ottawa, Boulder, and then San Francisco. The variance in the predictions varied based on the number of official count data that we had. We did not have the same sample for all cities. So for some cities, we also had data which were more dense in time and sparse spatially. But for the others, we had more spatially distributed samples, but less sparse. Less dense in time. So that's the map we got, and the thickest line, which is like very high, is predicting how much ridership happened in which parts of the city. The central district in and around the city of Tempe, where also the campus of ASU is located. It's a lot of student population that's riding their bikes, and then the outskirts where there are bike communities are also near to residential areas, closer to parks and such. So that's why the high ridership, and the rest of it is very distributed or heterogeneous. So in terms of understanding whether this can be replicated in other areas as well, we looked at Orange County area where we picked 2 different cities, which has very different demographic composition, amenities, access to more bike-friendly amenities. Let's just put it that way. It's more car-friendly versus bike-friendly. So coastal cities have more bike infrastructure, and also higher economic levels have access to greater amenities. So Newport Beach is a coastal city where there's a lot of bikeable pathways, but it's all along the coast, so it attracts a lot of recreational bicycles. The ridership volume is very high. And then Santa Ana is a mixed neighborhood where the income level is medium to low, but then also the crime rates are much higher than in Newport Beach. So you see my student Krista, she made this plot where we were talking about total crime incidents or density of crimes that happen across neighborhoods and how the ridership varies. So the most dense ridership areas that are the blue lines in this graph are mostly in low crime zones. So crime is potentially, hypothetically speaking, from this map, one of the factors that might affect how people ride. So this is just one parameter that we select. We did not look at any additional. But based on crime, we can just map it out and see visually how the ridership varies. And then also along the coast, so one of the previous variables, if you see, so distance to seashore is a variable that is there for San Francisco. For coastal cities, that is one of the determining factors of how much ridership will be there. So that probably or potentially influences how coastal cities see more ridership along beach parks and bike communities along the beach cities is much kind of well designed. Okay, so what kind of bike classifications do foreign countries have? They have off-street paved bike paths, they have on-street striped and signed bike lanes, and then class 3 is on-street shared lanes, signed bike routes. So all of these are shared amenities, not very well separated. The first one is the one that's mostly along beach or coastal neighborhoods, and then the fourth is also a cycle track, which is on the street but separated. So just by the composition of these amenities, we can see that the safer options are much sparser. So the fourth, if we say it's separate bikeways, much safer for bicyclists in terms of comfort or safety. The density of these bike pathways is not very high. It's mostly the type 1 and 2 bike paths that are commonly placed across the city. And this is again by income levels. So the poorer neighborhoods have more unsafe bike amenities. Because the safer neighborhoods will have more well-separated bike paths, which have, we haven't looked at speed limits, but we have looked at how much or the volume of ridership that goes through that particular type of amenity. So more or less low-income neighborhoods are suffering in terms of infrastructure when it comes to just bicycling. So this is a story map. I can share the link with you later, where you have the demographic variables, the income levels, and categorized by the bike. Okay. Sorry for the disruption. So I'm unable to share the story map link, but I can put it in the chat. So just coming to the policy implications of the ridership patterns, the four major findings from this is like, how can we improve sampling, the way we collect official data around counts for bike mapping in general, or bicyclist ridership mapping. And then how do we inform planners to use big data in a better way or a more implementable way? And then what are the hotspots of different ridership zones where we can come up with those areas where we can identify different categories of ridership, so very low, low, medium, high, and very high. And then also in terms of equity, so planning amenities for future use, we could give planners an essence of the first level of maps showing where amenities will matter more, who gets served more in terms of using those bicycles. So this is create a bridge and more people. So we got a glimpse of how maps will look like when you know there's data, there's amenities, and we want to map ridership patterns, but how do we capture different changes in ridership over time or in space? And can we map those again? So it's a mapping question for visibility. So what happens if there's infrastructure like this, but people are not safe. So does it really matter? Okay, so detecting the change and why infrastructure matters might help. So the next topic of discussion is then change detection and bicycle ridership from big data. In general, the broader impacts for this is definitely like how do you understand travel behavior in different cities, what kind of modes people are using, why they're using it, and making more targeted decisions about where to place amenities rather than just like implementing random things where people will never have access to those, but also comparing different interventions, like what happens pre and post this change. If a particular bike path is introduced or signals. So the different techniques for developing these change detection algorithms is not new in the sense from a computational perspective, but in the domain of monitoring bicycle change, this is a little bit novel, I would say. So how do you get the data in terms of showing where and how much changes occur? This is a map which one of my colleagues from UVic, Colin Fester, generated from bike maps. This map will show you like in time how many people are starting to use a bridge that had a new bike lane introduced. And more ridership was occurring on the right-hand side of the shore of the canal, and then there was a new path introduced. Wait for it, and then you'll see the whole city starts getting more and more connected with bicycling. So sometimes it's just connectivity that is lacking, and once you connect different areas, the usage patterns kind of start jumping up. So that is something that we still have to achieve. But what are the methodologies that can help build those questions for planners to better understand where to place? So how do we quantify change at the street segment level and map them at different levels of scale? And what unexpected changes could be identified that will need further investigation in terms of management of risk or safety perceptions people using these. So this is a little different in terms of developing a technology for bicycling mapping where you detect change at a particular time span. So we borrowed a concept from functional data analysis, which is a traditional field in remote sensing, where you map time series data, and the time series data can be at different temporal scales. So we used hourly and monthly data. The first one was capturing how the mean signature of that temporal pattern emerged for the hourly scale, and then the mean of the temporal pattern in the monthly scale. And then we operated on the functional differences of the transposed time series in the functional space, not the Euclidean space. The Euclidean space is generally like raw distances, but functional spaces you are warping them using a time warp function, which is on the right. So you are basically realigning those functional curves and then taking differences from the mean to see where higher energy changes occur. So this is a result of those warped functions. We could cluster them based on their differences from the mean. So based on clustering, how do we kind of group them? So we came up with 4 different clusters based on the variability around the mean function. And we did this for the hour and the month data. And the deviations from the mean was evaluated to categorize or come up with names for each classes because it's an unsupervised learning algorithm to gain this clustering. And we come up with typologies or names or nomenclature for this kind of temporal changes. So that was interesting because we grouped the segments by cluster. We came up with a mean function for the change. Using the variability difference for different cluster groups. And we also computed bicycle space load. And then we mapped them to come up with visual differences in how much change is happening at what time periods. So for the hourly, we came up with peak period and off-peak period clusters. So whether it was a high change or a low change during peak periods. And then for the monthly, we came up with seasonal differences. Whether it's a winter, change in the winter months or the summer months, and how much is it a low change? Four different categories, and then also overlaid how much exposure in terms of crash density is happening in areas which see a lot of high change. So if there's more infrastructure, does it necessarily mean more people are safely riding, or is the ridership increasing but safety is not accounted for? So that's a complex question, but we just use overlay. We did not do additional analysis for this particular country. And we found that high density areas where high crash is occurring also has a lot of high ridership changes. So necessarily people are increasingly using those amenities, but sometimes they're not just safe, or the time period when they're using those are not probably the best ways to kind of tackle traffic. So we need more safer infrastructure. So these methodologies are very quantitative methodologies where the community is somehow left out. So how do we engage more people to kind of basically understand why we need such infrastructure? So there's a tool called bikemaps.org. It's a citizen science tool. You can pull it on your computers. It's a collision detection sort of a tool where you go on the map, you drop a pinpoint, and you can say, hey, I'm the person who experienced a crash or a near miss, or I observed somebody who came up with such a crash or a near miss at an intersection or in a lane which has unsafe infrastructure. So that's up to the person who witnesses that kind of an incident or somebody who experiences that. So there's a way to use this tool for different purposes, and the type of incidents that you can record are citizen collision reports, near misses, if there's a hazardous location. For example, where there is a bike lane, but it's going downhill and the speed limit is not super comfortable for car drivers to slow down. So that's a hazard, and you can map that. You can also map bike thefts. That's an issue. I don't know how you see the examples where people steal bikes. It was very common in Germany where I was. My seat cover got stolen the first day I got it. Not a big loss, but it was something. Okay. Yeah. For students, it matters because bikes are expensive. Also, not super cheap. So I reused bike days where you can buy each other's bikes. Those days are fun. And then a new tool is there. It's called new infrastructure. So you can also pinpoint if a new bike lane is introduced, if you face a particular incidents around. And then how do we understand what's happening from this data? So you have a heat map like visualization for bike maps, which you can see the spots of high incidence. So here you see LA, Santa Ana, Beach. The ridership is high in Long Beach as well, but the density of incidents around bicycling is also kind of increasing. So what are the different types of incident reports that bike maps has recorded? It's mostly hazardous infrastructure. It's not always. There are a lot of near misses and a few thefts, but there are also a lot of collisions. So the highest amount of infrastructure related hazard is the kind of biggest chunk of the count that happens in our data from bike maps. So this is by the hour and by times of day during the week, how much incident is recorded, and between 2 to 4 p.m. that's the highest count. That goes up to around 25 reports, and this is just for the Southern California regions. You can also see it's not a very good informative time series because we don't have a lot of regions in SoCal, and we would encourage you to kind of record more trips because it's citizen science, so that we have more functional kind of information in the incidents for monthly basis. So this is where people who usually use bikes can get involved, communities can get involved, and they can also share their opinion about new infrastructure or proposed changes. The next topic, it's not just bikes, but it's also other public transit modes where people can use whether to choose a train or a bus or take their car or ride their bike or walk. And how do we detect that from data? So there's a method called transport mode detection, where you can combine different modalities of data from GPS, accelerometers. You can come up with a classification-based algorithm where you can choose which mode is the most, just from the raw information of where people are or how they're moving, just from the mobility patterns. So in terms of detecting modes, it's fine, but just GPS data or just accelerometer data is not a complete information for detecting these. You also need geographic context to identify which modes are more commonly used and why. So you have to answer the why question. Sometimes as planners, we need to answer that more than in other fields. So integrating geography in mobility studies is something that's not very widely done. It still needs a lot of research. And that can help us in two different ways. The first way is it can make models more generalizable, the understanding of the location where we are situating our study, how the geography is, how many people will actually use different infrastructure, and how their travel behavior is kind of modulated based on this contextual information. And then obviously from a modeling perspective, adding more context improves your modeling outcomes. So they become more accurate and you can use it for different cities. So this was the result from one of the big population JPG, where we are assessing the role of geographic context detection from GPS data, and we looked at Canadian cities because we had accelerometer data and GPS. We also added in context data from GIS tools, such as distance measures to transit centers or housing affordability and such, how many people are using buses. So those kind of information help you improve the accuracy of a model where you're just using solo GPS and accelerometer versus you're combining contextual data. So your accuracy improved by from 37 to 64% in Montreal to about 44 to 74% in Toronto, and then Vancouver is from 68. This was a collaborative research. It was funded by the CIHR and different modes like bicycle, bus, car, train, and this is a typical confusion matrix diagram that we come up with models. What's the true value of the mode? Considering a trip information based on GPS and accelerometer, and it's classified as a bicycle versus what is my model predicted? Is it predicted bicycle or is it predicted bus or walk, transit? So we matched the actual classification with the predicted classification. And we saw that for a generalized model, classification varies from 51% for walking modes, 62% for car, 85% for bicycling. But when we are using more context-specific models, the accuracy improves, especially for bicycling, it goes up to 99% in this case, and then 77% for another set. So this difference happens. One reason for that is how much data do we have that originally classified bicycling trips. If we had the original data set which did not have enough bicycling trips, your accuracy will not improve. So you have to have a well-sampled data set where you have all these 5 modalities. So more interesting parts of this kind of very heavily quantitative analysis. So functional analysis, how can it help you? So it can be used as a tool for temporal change detection. So time-wise, where more infrastructure or less infrastructure is improving the possibility of increasing ridership. And then detecting hotspots of safe neighborhoods where amenities are actually working for people. And those kind of information can be combined with the citizen science platform, tools that people are actually reporting. So improve infrastructure that require more safer, separated bike paths versus shared or shallow bike lanes, and how the temporal variability happens. So difference. So some of the ongoing research that I started after joining UCI is looking at spatial variations in charging demand. And especially we started with Orange County because that's where we are located. And this is kind of a data fusion based approach where we are also combining topography, road classifications, land use, and existing location of EV chargers, and calculating a cost-based travel time layer, which will give us a hotspot map like that. So which is the area that has the least cost associated in terms of access to EVs. So the red spots are the most accessible, the bluer spots are less accessible. So in terms of the socioeconomic characteristics, median age of our economic populations are 38.6, and then you have income, which is $90,000, which is not too bad. Owner occupied, there are more high income neighborhoods in areas which are more coastal than in the inland like Anaheim and Santa Ana. But in terms of understanding these EV charging station placements, we have to understand the demographic and the demand. So which neighborhoods do we identify using socioeconomic factors? How they contribute to the spatial disparities is something we wanted to question or hypothesize. And then what kind of machine learning algorithms will help us predict more charging station placements. And we wanted to also compare whether these predictions are more equitable in nature, which is not a very well understood phenomenon. This is a model-based diagram, but I'll just quickly go through it. It's like the kernel density estimation for placements, and then feature selection like we discussed in the bike study for extracting the most significant variables that can determine which information will help you assess where more charging stations you might find. And then finally, we use machine learning to quantify the spatial variables of charging. So in terms of the variability, we varied a spatial grid from 1 kilometer up to 5 kilometer, and we saw that the bigger the grid size along which we were predicting, the accuracy estimates were higher, but there was also higher variability. So if you make a very fine-grained assessment of spatial equity zones, your accuracy will be high, but it will not be very variable. It's very the variability is low in the sense if you change the socioeconomic factors or the contextual variables that predict these kind of outcomes, the uncertainty or the error around that will be more. So if you have more variability, your error will be less. So a better result is the 5 kilometer. So as we increase the spatial resolution, you have higher uncertainties, but you also have the spatial boundary around which that uncertainty can vary. So you cannot say pinpoint right here based something and it will work like magic. You have to say within an area of say 10 to 20 meter, we have predicted placement would help. So that's kind of the policy outcome or the planning from this study. We did not test grid sizes beyond 5 kilometer because that would lead to a lot of gaps in the data, and we did not have a lot of additional data from crowdsourced platforms and such like we have for bike studies. This is mostly DOE data from NREL, that's type 1 and type 2 chargers. And in terms of the equity assessment, these are the variables that we've used. I think earlier someone had a question about what variables we were determining equity. So number of vehicles in particular neighborhoods that are population density, average commute times, housing affordability, whether people live there or just come there for work. The demographic in terms of age groups, 25 to 45, minority population that reside in particular neighborhood, poverty levels, employment rates, education levels, and the current distance that a particular neighborhood is from the nearest charging location. And also, we include the pollution level estimates because we can't towards climate friendly transition in terms of cars. And household size, number of cars per household. And then traffic impact, how much traffic is there in a particular neighborhood, where people actually drive to that area to get their vehicles charged, or they need a more local charging option in their home. And these were the findings in terms of scale. So the low, medium, and high were the three equity zones that we predicted, and the total number of let me try to simplify it. So let's just say the first initial findings are that Santa Ana, Anaheim, Costa Mesa, and La Habra have the highest variations in terms of equitable access to charging stations. So how people how much they have to drive to go to a particular nearby charging location, or where they kind of need more chargers. And then 11% were predicted that lying in the high equity zone, and 20% were within the low to medium density basements. So the dark blue regions have the highest EV density, and the largest red spots have the highest inequities in terms of access to those zones. So it's kind of interesting that the density will also have some inequitable aspects to it. It doesn't mean that all of them are getting access to a public charging. Some people still have barriers to kind of ownership. The vehicle ownership is a big barrier. Even though there are chargers, they're not very well utilized. If people are using in multi-unit buildings, how many people have access to the nearest location? So these are not very well identified in the study. So there's scope to kind of develop this. This was an initial hypothetical pilot study, like we call. There's uncertainties around the predictions because of the limitations in terms of data, but we are looking at additional data from crowdsourced apps, which are collecting EV mobility patterns. So if that can be plugged in, it's going to improve further. And also varying the equity indicators across different geographies. So not just this Orange County area, what are the different defined factors in different locations across the place. So rural electrification would be a different kind of conversation because of factors and the distances to the nearest charging, the driving distances, and such would vary. So this is not the best estimate, but it's one of the estimates which can be a pilot to test for other cities. So we have to expand this study. It's still in the phase of ongoing research, I would say. Published, but it's also kind of the first pilot that we did. So there are not too many studies that identify equity indicators, especially in EV placements. And also the variables that we identified are not very rigorously used across a lot of studies. So that's to be determined in terms of how generalizable this is in terms of different studies. This is like the initial. And then when we talk about equity, there's a lot of controversies. We hear a lot of things. Some people are happy with the results, some people are not. But this is my advisor's paper, which came out in PNAS, and she talks very beautifully about empathy, equity, and ethics. So how we use the data ethically for most people. We should have a little bit of empathy for underserved populations, and we should have a lot of equitable discussions in planning in general. So this three things should combine how we kind of switch the discussion around equity in any field from a geographic perspective. So there's lack of data representativeness, which I talked about in the bike study. There's a lot of inferential error that can happen in pilots. Location privacy is an issue because sometimes GPS locations have like errors in measurement. Because the point it's showing, it might be off by radius of say 5 miles or so, just by virtue of the measurement. So it's a measurement error. And then open access to data and spatial science tools is something we have to talk as a community within geography, like how people can be involved in this kind of research. So democratization of data is what we call it. And then also inclusiveness in terms of data sampling and representatives. So coming to the last part, which is natural hazards. We just came out of a pandemic where people were very inequitably affected. And there are also hazards or natural phenomena, extreme events that also affect different populations differently. And transportation is a factor because when storms or hurricanes or floods happen, people's movements are disrupted and how they are disrupted is always not very equitable too. So where there are more, as you can see in the map on the left, it's a map for Hurricane Sandy where storm surge occurred, and we were using data from yellow cabs, so taxi trips in New York City. People were moving from A to B and how the trip times increased for certain areas versus others which were less affected. So one reason is the storm surge itself is causing floods. Some ways are getting flooded. People are unable to move around, but there are also inner areas where the trip times increase because of traffic disruption around the transportation network. And it's a network where if something is blocked, like you see in this figure, if something is blocked in the center of the network, it will dissipate, it will propagate along the network. It's not one thing that does not affect anything else. So that's a policy kind of aspect on it. So how do we monitor transportation during extreme events such as hurricanes and floods to kind of reduce disruption in terms of transportation practices. So the total trip distance was varying hugely before and after the storm hit, and how much time people were on the road, like getting from place A to B, exponentially increased. So this is data from previous and later sites, plus minus 15 days from the time of hurricanes. So these kind of changes are also being studied a lot in transportation planning in general. And next conversation is about vulnerability and what kinds of vulnerability we are talking about. So there are parameters like social vulnerability indices developed by the CDC, where they combine different aspects of socioeconomic indicators like socioeconomic status, household composition, minority status and language fluency, and housing type and transportation. And these factors are then normalized and aggregated to this strat level, which are mappable. And this was a map generated during the pandemic when we had data from the LA County on the COVID cases that were just happening, and how that variability in terms of infection rates started to happen, and which communities were in the early stage of the pandemic. It's not covering the full data set, but in the early stages of the pandemic, when there were no vaccinations yet in place, how this percolated across the country. So it was also a machine learning based study where we are relying on data from CDC, we were relying on data from the data portal from the county itself, and we mapped mobility indices and vulnerability indices across the whole country. Sorry. Okay. So in terms of accessibility, what were we looking at in terms of how many people are able to reach their nearest healthcare facility? So that's the transportation angle, and we identified a few variables. Maybe they're not the perfect measures, but vehicle ownership, whether neighborhood is walkable, whether there's a close by amenity around it, how many traffic collisions occur, whether there's a transit stop next to neighborhoods with low income and high number of populations that are kind of detached from these amenities. Came up with, again, the similar approach of least cost path, where we determine the social vulnerability index and then also determine the shortest path based on these accessibility indicators to reach the nearest health facility. So the map shows from low to high how the accessibility is. Okay. So finally, the built environment. People are familiar with LiDAR and how cars map their environment around it from such. So this is a visualization where a particular car is moving along the city. You have a LiDAR sensor on top of the car and it's mapping the entire neighborhood around it. And it can detect points where there's unsafe infrastructure. It can detect points where there might be potential hazardous incidents occurring. So this is kind of a new realm where things are going transportation-wise, and more methodologies are needed at this point to use such data to utilize them to make it more, I would say, actionable. So critical infrastructure monitoring, sense of bridges and such, how do we monitor heat stress and urban resilience context, and classified neighborhood vulnerability during wildfires. And the main research motivation was then, how do you extract features from these raw sensor data? So these are high volumes of data, and although it's mappable, it's not very well understood how we use this information. So it's basically location points across space in a very dense time and space module, but whether that's informing some sort of hazard, or how do you map it in terms of transportation detection, amenity and infrastructure monitoring is not very well understood. So we used LiDAR data to come up with a digital elevation model for building infrastructures. And then we also classified, so not a very good classification, but this is one that we started looking at, where we were looking at thermal imagery, LiDAR data, and aerial imagery, classify them into spatial clusters. And the clustering algorithm basically is a distance-dependent algorithm, where a weightage is placed on every pixel. So pixels which are closer to each other are weighted at a higher level than they are further away. And we use gift sampling as a model to kind of simulate from prior images based on the visible imagery, how good or bad the classification is. Okay. So one justification for using this method, it's a very non-traditional way of doing classification, because we did not have labeled aerial imagery. So it's not always easy to get labeled LiDAR data from XYZ. People will not provide it, especially not for academic research. But when you have to do some sort of unsupervised learning algorithm, and you want to do from a prior data set, you can construct that prior from a previously mapped image, and you can use that for probabilistic estimation of different mapped features. That's how we did it for the first run of the algorithm. And then these kind of methodologies, when it's built for the first time, it's a challenge, but once it's there, you can use it or situate it with different types of planning questions or policy questions. So how do you detect objects without prior knowledge of a particular neighborhood, whether it will work or not? What happens if there's critical infrastructure or power transmission lines that are broken down during floods or hurricanes, and how that can be reestablished quickly? So extreme events have a good implication in terms of using these methods. And just to conclude, my talk has spanned from a very broad perspective of public safety and infrastructure to also technological innovation, talking about privacy and social security. I hope you enjoyed it, and I look forward to questions.
You've given us a lot of topic area to dig into, so hopefully you've been thinking of questions along the way. We'll start in the room.
Question will be about using lasso. And before using lasso, like have you tried like other machine learning methods like random forest, like determine the very good importance?
So for the first study that I showed you on active transportation, it was not focused on comparing different machine learning models. It was focused on identifying features that inform bicycling ridership. And so I would say I did not compare random forest, but I also was on the lookout for a different approach which was not used in the literature. So lasso was not very heavily used in bike transportation literature. And that was my motivation.
One question like about safety, crime, like which parameters did you use? Measure the crime rate?
For the crime density?
Yeah, crime rate and density. Yeah.
So for which one? For the generalized models?
No, for the active transportation one.
So there were two crime densities mapped. One was just for Orange County. That was just a single
parameters that you use, like which parameter did you use for measuring crime?
Which parameters? Just crime count data.
Oh, I see.
So it's a density estimate from
Okay.
crime data.
Okay, I got it.
So it's the number of crimes reported to the police, and you got that from the database.
Thank you for your presentation. I had a doubt about in the bicycle or active transportation analysis, because you're using crowdsourced data, and usually that data is from people that actually use the bike, probably maybe cyclists, and so how would it be like you would be reinforcing and providing more infrastructure to the people that already use the infrastructure, and maybe you're not like capturing the people that are non-users, and how to like counterfact that fact that you're not getting the people that are not using it and maybe would not be happy with like maybe using I know because the most experienced cyclists don't like using some of the bike lanes. So like how to like involve those non-users and less frequent users.
So I think the first study that I showed you talks about bias adjustment factors. I think that is one way, but then other ways would be more qualitative surveys where you actually go to people and kind of get their perceptions about safety. So that we have not done. That's probably an opportunity to study. But yeah, I think getting very individualistic approach to why I'm not using will need a survey. It's not, since this was more data driven, comes from the secondary data sources that we have. We do not have access to primary data sources. We did not construct our study to go in that direction. We constructed it from a very different place. That's why the question might have seemed like we haven't addressed that, but adjustment factors were a way to kind of figure that out.
So I guess my complementary question would be like, so when you present this to like policymakers and decision makers, would you still advise them to do additional surveys? Because then what I fear is that you're already providing for people that already are using.
So bias adjustment was the question that we asked so that people who are already using the bike amenities or pro-bicyclists are not overrepresented in it. So I think that was a non-traditional way of hitting at that question, but I have not done the survey, so I cannot say how much it's going to be more. It's probably going to be more informative in very small groups where you are very sure, like these are the demographics that are very avid bicycle users, but these are the infrastructure that we do not have here. I think it could be extended in that way.
Thank you. It was great and huge. But one question is on the bias, correcting bias. By how much?
So I think one result that I did not show was the comparisons I showed. We don't know for sure. That is true, and I get that a lot. So this is the map of predictive accuracy, but there's another map for just the bias correction estimate where we predicted these volumes and we were off by a lot. This is the annual average estimate for the whole year. And then we were afraid that to give it out to the planners in the city itself because they did not have enough data where we were predicting. You cannot compare. This is just an estimate. It can be
What's
off
the
by
time
a lot.
frame?
It was 2017.
There's a space to go back and see, compared to real data. I mean, that would be fascinating to say, oh, but this is the variance. And on the charging stations planning, I guess I'm gonna email you, like, why do you choose those methods? Yeah, it's like it's gonna be a long.
Yeah, it's a lot.
Yeah, can I email you?
Sure.
Other questions?
I think my question already got answered. So.
I don't know if you'll be able to answer this question. It's very general, but the 3 E's that you mentioned, the ethics, empathy, and equity, in general for the field of like machine learning, big data, geographic information, where do you feel like those values are located? Like when you talk to your peers, like is it
do you feel like there's a small cohort of people like using the data this way, or is it like gaining prominence? It's more of like a
I'm
field
hopeful,
wide.
so I feel that I'm gaining prominence in the sense that data is evolving, right? It's an emerging technology domain where people are moving from a very like single based data collection approach to using these secondary data sources more and more. I think the way I see it is like how technologists and planners should work hand in hand to understand these three values. It's not just the data practitioner's solo game, or it's not the planner's solo game. So it's a joint kind of understanding where, because if we give out results and we do not go back and talk to the planners, how this is being implemented is still a question. So it's not a very good answer, I know, but that's to the best of my knowledge.
Take a question from
Yes, there's just one question. It says, how do you think that we can use big data to monitor VMT in a way that is consistent across different areas?
Probably if there's a layer provided by the city, yeah, it's very good.
anything else from the room? So I think we'll take this opportunity to thank you again, Avipsa, for sharing all this, and I know there'll be some follow-ups, so thanks again.